Assalamu alaikum, this is Hamad Ali with another video of DSP. Today is lecture number 6 and the topic of discussion would be sampling theorem. First of all, looking at the definition of sampling. Sampling is the process of conversion of a continuous time signal to a discrete time signal. For instance, if we have a continuous signal and we want to convert it into a discrete time signal, and the process to achieve this kind of result would be known as sampling. Let's consider a signal, continuous time signal, in which m of t is the message signal and its Fourier transform would be given like this, where omega m is the maximum frequency component of m of t. Now let's consider another continuous time signal, that is the impulse train, where ts is equal to sampling interval, omega s is equal to 2 pi over ts. This omega s is known as sampling frequency. So as we discussed earlier, omega m is the maximum frequency of the message signal, and now we are dealing with omega s. Omega s is the sampling frequency. So the c of t, that the impulse train, would look like this: summation from n is equal to minus infinity to infinity delta of t minus nts. Now we'll put different values of n and then see what value of c of t we are obtaining. First of all, if we put n is equal to 0, c of t becomes summation from n is equal to minus infinity to infinity delta of t, which means that the impulse present at origin. Now if we put n is equal to 1, then c of t becomes summation from n is equal to minus infinity to infinity delta of t minus ts, which means that the impulse is present at t of s. Now after multiplying the two continuous time signals, that is m of t and c of t, we obtain a signal like this. This signal would be known as the sampled signal, and its expression would be like this: sigma of t is equal to m of t into c of t. As we discussed earlier, that we'll multiply both the continuous time signals. One is the impulse train c of t and the one is message signal m of t. Now if we are to obtain the spectrum of sigma of t or delta of t, we'll follow the following procedure. First of all, the Fourier transform of sigma of t is given by sigma or delta of omega. As we discussed earlier, that delta of t is equal to m of t into c of t. So now we have, if we want to multiply two signals, the Fourier transform is given by. Now as we know that if we are multiplying two signals in time domain, they would be convolved in the frequency domain. That's what we are doing here. If we multiply two signals m of t and c of t in time domain, we obtain delta of omega is equal to 1 over 2 pi m of omega convolved c of omega in the frequency domain. M of omega is the Fourier transform of the original message signal. C of omega is equal to omega of s summation n is equal to minus infinity to infinity delta of omega minus n omega s. By simply putting in the value of c of omega and m of omega in this expression, we obtain delta of omega is equal to 1 over 2 pi into m of omega convolution omega of s summation from n is equal to minus infinity to infinity delta of omega minus n omega s. Now upon rearranging, we obtain this expression. By using this property, x of t convolution delta of t minus ts is equal to x of t minus ts, we obtain a simplified version of the delta of omega expression, that is 1 over ts is equal into summation n is equal to minus infinity to infinity m of omega minus n omega s. That's a simplified version of delta of omega expression that we obtained using this expression or this property. Now what we'll do is just simply put in the values of n to obtain the values of delta of omega. For instance, if we put n is equal to 0, we'll simply get m of omega. If we put n is equal to 1, we'll get m of omega minus omega s. If we put n is equal to 1 minus 1, we get m into omega plus omega s. So the waveform of m of omega would look like this. As you can see that these portions of the waveform are far away from each other. They are not touching each other, neither they are overlapping each other. In this expression, omega s is the sampling frequency and omega m is the maximum frequency of the message signal. As we saw in the first case, omega s minus omega m is greater than omega m, which implies that omega s is greater than 2 omega m. So in this case there would be no overlapping. Now let's consider another case. That's a second example in which the samples are just touching each other and omega s minus omega m is equal to omega m, which implies that omega s is equal to 2 of omega m. So there would be no overlapping in this case also. Let's consider another example in which the samples are overlapping each other. In this case, omega s minus omega m is less than omega m, which implies that omega s is less than 2 of omega m. In this case, there is overlapping and you cannot recover the continuous time signal accurately, whereas the samples in which there is no overlapping, they can be recovered easily. Now let's come to the final statement of the sampling theorem, which states that a signal can be represented in its samples and can be recovered back when sampling frequency is greater or equal to the twice of frequency component of the signal, as we discussed in these cases. So hopefully you have understood the concepts of the sampling theorem. That's all from today's video.